Hi Class A, I feel like I'm here with you right now. So I want to start with actually going over one problem from the homework. We're going to go over number 43. We have y is equal to x cubed plus x squared minus 2x minus 2. And this problem is a factor by grouping problem. So let me pause for a second. So the question asks to use a sign analysis and your knowledge of end behavior to state a graph, a probable graph. So if I factor this, I know that I can group this and I can group this together. First I can pull out an x squared and get an x plus 1, and I can pull out a negative 2 and get an x plus 1. So I get y is equal to, and if I factor that I get x plus 1 and x squared minus 2. This tells me that my critical values are negative 1, and this would actually give me plus or minus the square root of 2. So, given that, I can state a sign test, and I have negative square root of 2, which is like negative 1.4. I have negative 1, and then I have the square root of 2 as my critical values. If I test a very, very large number, then on the right side, I get a positive number, because I'm going to have a positive times a positive for a very large number. And that means that my signs, this is positive, my signs are going to alternate, so it's going to be positive there, negative here, negative here. Furthermore, if I look at end behavior, I have a leading coefficient of a positive number, so it's positive. And it's an x cubed, so it's an odd. So my end behavior should look something like this, which matched the top left graph from the end behavior ones. So piecing that all together and knowing that my critical values are actually also my zeros. These right here represent my zero. Okay, that was me trying to do a clever circle. These are my zeros. I can do a graph and get a pretty good sketch going. Let's make it so that, actually let's change the grid a little bit, because that's too much. If I get a graph like this, I have a root of negative 1, a root of negative 1 radical 2, and a root of positive radical 2. And so my graph is going to cross, coming from the bottom left, it's going to cross again, and it's going to cross again there. Crossing here, and crossing here. So that's a pretty good sketch of this graph. What I would want to see is that it crosses the x-axis 3 times in those spots, going from the bottom left to the top right. And then you could graph it and kind of confirm that. So now we're going to head on to some new stuff. We're going to talk about concavity. So concavity, hang on, sorry, I'm just pulling this up on me. Concavity. Okay, I can't spell right now. Is the curvature of a graph. And it can be concave up, or it can be concave down. So when I think about concavity, I think about a cup of liquid. And if I complete the graph, is liquid emptying or is it liquid filling? Here's what I mean by this. Let me show you 4 examples. So we're going to draw 4 grids kind of across each other. I'm actually going to turn off the graph paper because I don't necessarily want that right now. So I'm going to draw 4 grids just kind of right by each other. Okay, well, there's 1, 2. Ooh, let's see if I can do this. Kidding. Why is it doing that? There we go. That was less clever than I thought it would be when trying to copy paste. I know, it probably would have been faster just to draw the 4 of them. Okay, zoom in again. 4 grids. So the first one I'm going to show, actually the first 2 I'm going to show are concave up. And this is also going to be concave up. I'm going to show a graph that's increasing, and it's concave up. Here's a graph coming from a point down here that is increasing, and it's concave up. That's actually usually going to be a piece of a graph. that's concave up. So how can we be decreasing but also be concave up? If we kind of come like this and come down here, that is a piece that is, I should just put points at the end, or just anything, that is decreasing but also concave up. And here's why. If I were to take these two pieces and join them, they actually would become a cup that I could then fill with liquid, and the liquid would stay in the cup. So both of those are concave up, with the piece on the left here being the decreasing one and the piece on the right here being the increasing one. So let me move that piece back over to where it started. We also have concave down. So this is concave down for both of these. And with concave down, I have increasing and decreasing as well. So my increasing for concave down would be something like this. Now I want you to compare the two increasing ones right now. They're both increasing from left to right. As my x's get bigger, my y's get bigger, but they're doing so differently. And then my concave down decreasing one would be this. And if I took those two pieces and joined them, the cup of liquid would empty. And an emptying cup of liquid is a concave down. So that's sort of how I use to piece together what's concave up and concave down. And this is going to take a little bit of practice, because you're going to have graphs that have regions that may contain all of these. Turning points, we can't call them turning points anymore between concave up and down. We're going to call points of inflection. Points of inflection occur where the graph changes concavity. Where the graph changes concavity. So let me show some examples of points of inflection. I'm going to do two grids right by each other, or side by side. And here's a grid with, on the left here, let's do a region like this. Let's go like that. That's a bad example. Well, let me try drawing that again. That's better. So ignoring the grid right now, somewhere in here we have a concave down, and somewhere in here we have a concave up. So right in this middle region, somewhere in here, we have a point of concavity. And I'm going to call that point of inflection. And here, this piece here was concave up, looks like a cup, and this is concave down, looks like an upside down cup. So points of inflection, there's something that we're going to kind of guesstimate as best we can for a little while. There is a way to figure them out, but it involves calculus, which is part of why we're learning what they are right now. Let me show you another graph. This is a graph that has two turning points. We call turning points local maxes and local mins. Actually, I put those in opposite order. Local min, local max. But then we're going to mark some points of inflection. So I'm going to take a thicker pencil and I'm going to sort of sketch on here everywhere that is concave up. So here's an up cup, cup, cup. This is a cup. This is a cup that's still holding liquid. And right here, somewhere in here, it changes. So this right there is a point of inflection, a POI. And then the next piece is all a downward cup. So one way to think about points of inflection too is they have to occur in between two turning points. I have a turning point up in there and down there, and somewhere in that middle I have a point of inflection that changed from concave up to concave down. So we're going to do an example here, and I'm going to want you to draw this on your own graph paper. So I'm going to turn the grid back on, and I'm going to do a very large graph. So walk with me here while we sketch this, because your sketches are going to be really important. I want you to practice sketching some of these. Otherwise, I would just give you a handout. So I'm going to mark this as -1, -2, -3, -4, 5, 6, and -7. And we're going to put a point at negative 7, 0. That's ordered pair negative 7, 0. Then I'm going to go 1, 2, 3, 4, 5, 6, 7, and put a point at positive 7, 0. I'm going to put a point here at negative 2, 0, put a point at 2, 0. Then I'm going to go down 3, put a point at 0, negative 3. Then I'm going to go to the right. Let's go to the right 4.5. I'm going to put a point here and go up 4. 1, 2, 3, 4. I'm going to put a point here. Trying to make sure you can see that. Then I'm going to do the same thing over here. And then I'm going to do my best to connect them with what looks like a piece of a sine graph. It's not precisely a sine graph because we're not evenly proportioned throughout the whole thing, but I get the idea. Okay, that's okay. So by the way I've drawn this, I could ask a few questions. I'm going to shrink this just a little bit. And I'm going to ask the question, first of all, A, give a region where it is increasing. What are all the regions where it's increasing? Well, I'm going to highlight these. Here's a region where as the x gets bigger, the y gets bigger. Here's a region where as the x gets bigger, the y gets bigger. And I think that's it for the increasing. Increasing are areas in between turning points. Same with decreasing. So when we look for increasing, decreasing region, we're at areas in between turning points. So my increasing would be from negative infinity to negative 4. And we're not going to include the negative 4 in that. Union. And we're going to go from 0 to, sorry, that's negative 4.5. And then 0 to positive 4.5. My decreasing regions would be the opposite of those. It'd be from negative 4.5 to 0, and then from 4.5, sorry, union, 4.5 to positive infinity. Okay, then we look for concave up regions. So my next one is going to be, where do we concave up? Well, it would be helpful now to erase the highlights because the highlights aren't really telling me much. If I assume that the arrows continue where they're going, concave up would be everything from here. This is all, or sorry, that's concave down, but I'm going to highlight the down ones anyway, all the way to there. Right at that point, we're actually switching concavity. And I'm going to now highlight in yellow a part that's concave up. This is concave up. This looks like a cup. And everything in here is concave up, and then, we're switching now to concave down again. So yellow highlights are concave up, blue highlights are concave down. Concavity also doesn't include points of inflection, so my concave up would be from negative 2 to 2, and concave down is from negative infinity to negative 2, and from positive 2 to positive infinity. It's all the blue highlights up above. Lastly, if I look at the graph and I've kind of identified points of inflection, my points of inflection would be, there will only be 2 of them, and there are areas in between where we change from concave down to up or up to down. It'd be the ordered pair negative 2, 0, and 2, 0. This can be confusing because these are actually ordered pairs. They're not intervals for interval notation. Okay, so that's a little bit of analysis of this. I'm going to call that number 1, and I'm going to look at number 2 now. As we just said, we have 2 points of inflection. And I'm going to take these and move these down here. You can rewrite them if you want. But we also have 3 turning points. Our turning points occurring at negative 4.54. So I have negative 4.5 comma 4. Oops. I have 0, negative 3, and then I have 4.5, comma 4. So, okay, let's kind of end that one. Let's do another one. Shoot, this problem. Oh, let's give it a letter. Let's call that A. So then we're going to go to the next one. We'll call this B. I'm going to give a polynomial p of x with 3 turning points at negative 3, negative 4, 0, 2, and positive 3, negative 4. And also with 2 points of inflection at negative 1, 0, and 1, 0. And I want you to sketch this. So the sketch of this is going to be, well, we're going to need this and plot all those points. So negative 3, let's see, negative 3, negative 4, 0, 2, 3, negative 4, negative 1, 0, and 1, 0. So if I put that together, and I have each of the, I should put points in red. These are turning points. And I don't know anything else about the graph. I can say this. I can say, for sure, I know the graph is going to have to do this. Oops. Because I know that that's a point of inflection where I start and end what is essentially a concave down region. And then I know I must also now transfer to go to be a concave up region. So it's going to turn there and continue. Turn there and continue. Notice how the information didn't tell me anything about x-intercepts. We have 1, 2, 3, 4 x-intercepts. But the outer 2 it didn't really tell me anything about. Now this is something we can comment on here. I can say there are in fact 4 zeros. Zeros, x-intercepts, and roots are all the same thing. So that could be a question that I ask. How many zeros must this contain? Now, there's a few other things. How do I know that this doesn't turn? Well, if it turned, we'd have another maximum. I'd have another turning point, and I don't have another turning point. Same thing with the right here. I know that has to continue up, because if it turned, I would have another turning point. It doesn't give me one. How do I know that this goes like this and doesn't go like that? Well, because if it changes like this, that's a point of inflection. That changes concavity from concave up right here to concave down right there. That's also the difference with what you guys have been noting with square root functions. Parabolas are concave up. Square root functions are concave down. Okay. Next thing, we have this thing called the intermediate value theorem. This is very valuable, and this helps us identify some zeros. The intermediate value theorem. So, we're going to consider, which is another math way of just saying think about, consider p of x, a polynomial, and the closed interval a to b. So I'm going to sort of sketch this out below so we can kind of get a visual for what the heck I'm talking about. Okay, here's a graph. Let's say I put an A here, and I just put a B here. It doesn't matter where they are. And I'm going to put a point here, and I'm going to put a point here. So here's a graph that has a closed interval from A to B. So I'm just going to go closed interval. Okay. There's a graph. Closed interval A to B. For any value C between P of A and P of B. So let's mark those on the graph. We have P of A is right here. That's like the Y for that A value. Oops. Sorry, that's not P of A. I don't know where I thought that. It's the intersect point. It's getting late. We had open house tonight. My brain's hurting. Okay, this is P of A, because that's the Y value when X is A. And then P of B is right here. There's P of B. And it says for any C value in between P of A and B. So I'm just going to pick a C value here. We'll call that right there. So there's a C on the y-axis in between P of A and P of B. For any value C in between P of A and P of B, there is at least one x value in the interval A to B such that P of x is equal to C. Well, according to this graph, I can find it. It's actually right here. And here's an x. So this actually means that there has to be something in between. The intermediate value theorem is called the in-between. It just means that in between 2 points, you cover everything in between those, for x and for y, as long as they're connected. So let me give an example of this. I'm going to sketch another grid. I'm going to put the point 1, 2, and 4, negative 3. And I'm going to connect and kind of draw through those. There's 1, 2, 4, negative 3. When x equals 1, f of x is greater than 0. This makes sense. We have a point here. I'm actually going to erase that and say here we have a point. When x equals 1, the y value is greater than 0. When x equals 4, the y value is less than 0. I know that that's true. When x equals 4, boom, that y value is less than 0. So since here I have a point above and here I have a point below, and I know that these points have to connect, somewhere in there we have at least 1, 0. Now we could have more than one. I could have a graph that goes like this. But I am at least, and I should say, we are guaranteed at least one x value where f of x is equal to 0. So here's kind of the real gist of this. I'm going to rewrite this theorem. I know, I'm doing this 3 times, and this should tell you how important this is. Given any polynomial function, or given any poly, if you know that P of A is negative and P of B is positive, then there must be a root remember, root 0 x-intercept between A and B. Okay, an example. If g of x equals negative x to the 4th minus 2x to the 3rd plus 4, and f of x equals x squared plus 1, use a graphing calculator to solve g of x equals f of x. Okay, I'll let you guys pull out your graphing calculator and do this, and I'm going to do this as well. I'll pause the video while this comes. So here's my initial graph. Let me change my x scale to something a little bit more tighter so I can see this better. Let's change that to -4. Okay. Let's just look at the blue graph for a second. If I look at the blue graph, I see a point up here where my finger is, and I see a point down here. I actually see an infinite many points, but all I'm saying is that with the intermediate value theorem, if I have a point up here and I have a point down there, then somewhere in between these 2 points I have to have at least one x-intercept. It's got to cross the x-axis for it to make it from up here to down here. Now, I know those points aren't marked or anything, but this is just what I want you to see. Let's go back to the question now. The question is a little bit more of an expansive question. It just wants to find the x values where these two functions are equal. So once again, that's your intersection mode. You guys will do a second calc intersect, and I will just go to the menu and say Analyze Graph and Intersect. And I find an intersection point here. And I find, let's do it again, find an intersection point there. So if I round my x values, I can say that that means that x is equal to negative 1.91 and 0.91. But the second question is a little bit more clever. If I say solve negative x to the fourth minus 2x cubed plus 4 is greater than x squared plus 1, and I look back here, it's kind of helpful to say, okay, so this one's the blue, and let's see, the other one is the red. Well, let me see if I can snap this and get a screen clipping of, no, not that. Oh, I was so close. Sorry, this will take 2 seconds. There we go. If I want a screen clipping of this, and I say, okay, well, we're going to solve this, where's the blue greater than the red? That means where are the y values for the blue greater than the y values for the red? And I believe that to be this region here. That's everywhere that the blue is greater than the red. So my interval would be from negative 1.91 to 0.91. Oops, not brackets. It's an interval and it's greater than, so we can't include it. So that's the interval notation. Okay, that's it. Homework 4.1 to 4.2b, page 283, 1 through 6, all 18, 20, 25, 26, and 32. See ya.